Today we're going to talk about exploring robustness in dynamic graphs. We'll be talking about dynamic graphs. We'll talk about what they are and a little bit about a theory and some examples. And then we'll talk about robustness. What is robustness? How do we measure it? And then we'll do some exploration of robustness in dynamic graphs. So in order to talk about dynamic graphs, we need to cover a little bit about theory. We'll talk some examples, and then we'll get into some issues that arise with algorithms and representation. So we begin at the beginning here with graph theory, and we know all about graphs. They are made up of vertices, which represent components or things, and then there are edges or links that represent relationships between those things. And then sometimes we have directed graphs, which indicate the direction of a relationship. And sometimes there are weights on those edges, or sometimes there are weights on the vertices, and those are generally used to reflect something like a cost or an expense to traverse something or to use something somewhere. So then, what is a dynamic graph? Well, quite simply, a dynamic graph is a graph that changes over time. It has the same components, vertices, edges, and weights, but it adds this changing component and this temporal component. If we look at an example here, we have a small little graph of about 5 nodes, and as we progress across a small span of time, we see some things change in this graph. We delete some nodes and remove some links, and then we add some nodes and then add some new links. And so the graph we have at the end doesn't look the same as the graph that we had at the beginning. Real-world examples are everywhere. In fact, some of them really appear to be quite obvious, like computer networks, communication networks, and social networks, where things come and go and change all the time. We add computers and networking equipment to computer networks, and so those networks change, and then we have social networks where we add new relationships, new friends, new acquaintances, where we add a new relationship to a business or a school. And these are two primary examples of dynamic networks, but they are everywhere. So if we look at just a simple little example of a transportation network, we know that the way the transportation networks operate is they connect places. So we have here a picture of a city with different places. We have businesses and universities, and then we have new development, and we're showing here roads and railways. And those are the links that connect those different places. And when there's a place that's disconnected, we extend a means of transportation to reach it. And when new things arise, there's new development in an area, we extend the transportation to reach that. So we talk a little bit about graph theory here. We talk about types, classifications, and we'll talk a little bit about models. So there are different types of dynamic graphs, and the type is used to reflect what's changing in the network. So we have node dynamic and edge dynamic and weight dynamics. And if we have one of those, it reflects what types of things will change in the network over time. And we can have combinations where you have one or two or all three of those things were changing. Then we talk about classifications, and the classification is used to indicate what type of operations will occur or are allowed on these dynamic graphs. And it ranges the spectrum from fully dynamic, where anything and everything could change, to partially dynamic, where maybe only one thing or one type of change will be allowed. There are a couple of interesting models that I came across during the research. One is called the TVG model, and this is a bit of a mathematical, a bit of a formal model, where it looks a lot like what we saw with graph theory, where we have a set of vertices and a set of edges, but the model extends to include this time span, and the time span is used to indicate the lifetime of the system. And then we have these additional function arguments that are used to provide what we call a presence function and a latency function. The presence function's purpose is to cross the edges and the vertices with time, and then when asked, they'll give an answer whether or not a particular component was present in the graph at that time. So we can ask a presence function, was the link between node A and node B present at time 5 in this graph? And similarly, we can do the same for vertices. Barabasi extended the Barabasi-Albert model a little bit to address some real-world issues. So the basic BA model was somewhat static. It was a dynamic graph in that it added components, it added nodes and edges on an iterative basis. But when the construction was complete, the graph essentially is static. So recognizing that, the model was extended to capture different phenomena that happen in real networks. And some of them are initial attractiveness, internal links, node deletion, accelerated growth, and aging. I'll talk just about one of them. Initial attractiveness was a kind of an interesting one. If you think about a node that's added to a BA model graph, if it has 0 links, then preferential attachment will never attach to that link, then attach to that node, because the likelihood of attachment is based on a node's degree. And a node with degree 0 will have a 0 chance of any type of attachment. So what initial attractiveness does is it adds a component to the preferential attachment probability that gives every node a chance, even disconnected nodes a chance of being connected to. Now, one of the issues that comes up with dynamic graphs are related to various algorithms on graphs. We can compute diameter, we can compute degree, average degree, we can compute community structures and so on, and we can compute the shortest path between nodes. And in a static graph, you run that once and then it's done, it's complete. You don't ever have to run it again because the shortest path between node A and B will never change. But in a dynamic graph, nodes can come, links can go, and so on. And so the path from node A to node B at time t1 may be very different than it is at time t2, if the two are even able to be connected at that time. And so the issue is, how do we keep the shortest path accurate and up to date all the time? Well, we could recompute every single time. We could recompute whenever we're asked to find the shortest path. Or we could recompute every time there's a change. But either one of those are going to be really expensive, particularly for large graphs. So what we need to do is adapt the algorithms to be able to update in response to the different changes that are happening in the graph. And so there's a bunch of different approaches to doing this, but basically it boils down to when we know something is changed in an area of a graph, we're able to invoke a function that says something has changed, or recompute just this portion of the solution. And so it kind of minimizes how much work needs to be done on each iteration of a different type of change. Now, representing dynamic graphs gets a little bit tricky. It's not just as straightforward as having an edge list or node connectivity, or even just a simple adjacency matrix. However, the adjacency matrix is a really convenient approach for representing a graph. In particular, we can use it in dynamic graphs to represent a snapshot of the dynamic graph at any particular point in time. And then we can accumulate these into a sequence or a matrix or a list of adjacency matrices, and then we have a representation of the dynamic graph across a complete span of time. And whenever we want to see what did the graph look like at a particular point in time, we can index that for that particular time and retrieve the adjacency matrix for right then and there. Harari introduced a kind of interesting concept of using logic programming to represent a dynamic graph. And he essentially puts out the idea that we can use facts and rules. So we're talking about logic programming and predicate logic and rule-based type programming, where we can use facts to represent different artifacts in the graph. So we can have a fact that represents nodes, we can have facts that represent links. And then we can apply rules to say, well, given a particular question or given a particular problem, like reachability, we can construct a set of rules that will answer the question, is T reachable from node S? And then apply the rules, run the rule program, and it will tell you whether or not it's connected. Robustness. So we want to talk a couple things about robustness. First, we want to talk, what is robustness? Well, in short, it's really, how does the graph stand up when things are changing. And in particular, how does the graph stand up when some maybe perhaps drastic things are changing, like different faults? And a fault could be either just a random failure, like a particular node, a certain node, a random node or a random link fails or is removed or deleted. And then there's the targeted attacks, where specific nodes or links are removed or eliminated. And what robustness tries to answer is, well, how does the graph or how does the network stand up? Is it still able to perform its function when these problems are occurring? Now, how do we evaluate robustness? Well, Albert, Jung, and Barabasi in Error Attack and Tolerance in Complex Networks came up with, well, the concept of tolerance and determining, under certain conditions, failures and attacks, and using certain metrics, how do particular networks stand up? And they determined, a network may be tolerant or vulnerable to either attacks or failures under certain conditions. Now we'll get into the exploration portion. So I went through a series of steps here to try and learn and find some interesting things. And part of the exploration was an evaluation of different software packages and libraries in the Python ecosystem. First started looking at NetworkX to see if it had any support for dynamic graphs. And it had very, very limited capability in that space. Then I found this interesting library called Dynetics. And it was built on top of NetworkX, and they add some dynamic nature, some dynamic network processing. It was interesting, but it had some limitations, and it didn't fit quite with what I wanted to do, in the experiment of robustness in dynamic networks. In particular, it doesn't support deleting of nodes. NDlib is really more about network dispersion, and so they have epidemic models. It's built by the same group who wrote Dynetics, and so they behave very similarly, but it's much more geared towards like epidemic modeling. Gephi, I found, had an interesting plugin that allows you to do dynamic operations on graphs and networks within Gephi. And you can drive it, you can program it externally as an interface that you can send messages. And that was really interesting, and so we'll pursue that. We'll show you that in the demonstration portion. And then Cubix was a really interesting looking software package that I didn't quite have enough time to look at. But it operates on the basis of dynamic graphs being a matrix of adjacency matrices. And it has some really interesting visualizations, some 3D visualizations, this cubic visualization that allows you to inspect and analyze a dynamic graph from different dimensions. You can inspect the time dimension. You can look across time and visually see changes in the network. And then you can slice it and look across a particular node or particular connections and see different things there. I'm definitely going to spend some more time with that in the very near future. It looks really interesting. Okay, so the experiment that I wanted to perform was using spreading as a measure of robustness. Can we determine how robust random networks or scale-free networks are when they become very dynamic? And given the tools and libraries that I found, I decided that I should probably do a lot of the work myself. And I was able to use Jupyter Notebook to drive this, and use NetworkX and Gephi for visualization. Use Gephi for visualization and use NetworkX for the underlying graph model. And then I came up with different scenarios. Spreading by itself, so essentially spreading on a static network as a baseline, and then had additive and different detractive processes to it. So there's random detractive processes to simulate those random faults and failures, and then targeted attacks, to really simulate, if a network is under attack, and then increased that into very invasive attacks or targeted attacks on a network. And what I found out, so along the left column here are the different scenarios, and the two columns with the graphs show how the different networks performed. So we can see the red line, it's kind of small, but the red line shows the spreading, and then the blue line on the graphs show how many nodes the contagion or the message has spread to. Now there's a lot of scenarios here. I won't have time to show all of them, but we can take a look at a couple of them. So the first one I'm going to show here is a demonstration of spreading only on a scale-free graph. So what we'll do here is we'll start running some of these nodes in the notebook here. So we're creating a graph. We just created a Barabasi-Albert scale-free network here. And there's the distribution. And my fit line is a little bit funky, but basically we can see that there's a lot of nodes with very small degree, and there's a few nodes out here with a pretty big degree. So next thing we want to do is we want to show this network in Gephi. So this is using an API into Gephi and some Python code that I wrote that was modeled off of another project. And if we run this, here we can see now the nodes start showing up in Gephi, and now all the links start showing up. And it's kind of neat. You can kind of see the network building itself here. And once it gets all done, we'll be able to see, we can pick out different nodes here. We can change the color based on degree, try and pick out the hubs here. We change the size. Okay, so now we can see these dark blue nodes here. These are some of the bigger nodes in terms of degree, so we know that these are the hubs. So in terms of a spreading process, once we infect these nodes here, then we should see things spread probably really rapidly across the network. There's another one up here. Drag these out so that we can kind of see during the simulation when they get infected. Okay, and we can see here, yeah, so the big nodes here are in the upper 70s and lower 80s in terms of degree. So they're not quite reaching each about 1/5 of the graph. Close, but not quite. So if we run the simulation now, so the simulation will pick one node and as the origin for infection, and then apply the spreading process. And the spreading process is really simple. It just finds the infected nodes, and then in the next time cycle, it infects the neighbors, all the uninfected neighbors of those nodes. And I color them red so they're easy to find. So here's our seed node. There's the origin, and that one is connected to. It's not connected to any of the hubs, it looks like. So this could be maybe a little bit slower spreading. Well, there we go. We had several of the hubs, and now, wow, we can see the spreading go really fast, and it probably tapers off pretty quickly there once we've infected all the nodes. Okay, now we can show results in a tabular form, and here we can see it really just took 4 time iterations to run, and in the 3rd time iteration here we hit pretty much the bulk of the network. And by the 4th time iteration, we were pretty much all done. So here we can see that the spreading occurs really, really fast. And in sort of what we've seen in class, once we hit those hubs, it's a short number of hops to the hubs, and then once we hit the hubs, it spreads really quickly. Now the next demonstration will be spreading with an extremely invasive detractive process on a random network. And the reason I chose this one, as we'll see once we get back to some of the results, is that this is the one scenario in everything that I ran where I saw some really radically different behavior. And so once we create the graph here, we'll take a look at some of the characteristics of the graph. The degree distribution looks fairly normal with my funky fit line there. Now if we come back to Gephi, and let's populate the graph. Here come all the nodes and all the links. And one of the first things we observe here is that, as we know, the density of links in the random graph is less than that in the scale-free graph. And that's why we looked at the scale-free graph and it was really dark because there were so many lines for all the links. So now we'll look at the top degree nodes. There's a bunch of nodes here with a relatively high degree, 14, 13, 12. And this is showing us, again, a different look at the degree distribution here. Now, the the simulation process here, we're going to add nodes, and we're also going to remove nodes with an extreme invasive process. So the extreme invasive process here is it takes the top 10% of the nodes based on degree. So that's really, really invasive. So we have a graph here of 500 nodes. So each time we run, we're going to remove 10% of the nodes. So all of the nodes with the highest degree are going to get removed. And the additive process, to sort of compensate for that a little bit, is going to add 50 nodes back. All right, so if we run this, we'll see here's our seed node. And the seed node we can see is connected to just 3 other nodes. And so the spreading will start, but it's be fairly slow because it's going to go from this node to the other nodes. Now the blue nodes are the nodes that are getting added back, and the red nodes are the infected nodes. So here we can see, things are kind of moving fairly slow. Then we see the big detractive process. And some of this is a little bit of lag and Gephi, but here you can see the graph is really changing rapidly. There's a lot of blue, and so a lot of nodes are getting removed, and the spreading is really, really slow. But what we see eventually is that the spreading catches up. So if we watch, we see, well, the blue and the red really start to balance out. And then we begin to see, well, more red than blue. And eventually, once the graph settles out here, once we finish up the 10 iterations, we'll take a look at the results and see how we did. Okay, so it's all done. And so we see some black nodes. And the black nodes would be original nodes in the graph that were never infected. The red nodes are infected nodes, or nodes where the spreading has got to. And the blue nodes are new nodes that have not been infected. So some of these nodes, well, they have a fairly low degree. It's just a degree of 1. And then there's black nodes down here. This one has a degree of 2, but he's connected to 2 red nodes. So he probably would have been infected if there was one more time iteration. And here's a black node with just 1. And are there any nodes? Some nodes in here, some of the black nodes may have a degree of 0, and that's sort of how they survived or how they didn't fall victim to the spreading process. Doesn't look like that happened this time. But that generally happens in the random graphs. There's usually a node or 2 or 3 that don't get connected. But this was a very dynamically changing graph, mind you. We were adding and removing nodes, and with each addition we were adding links, based on the average degree of the graph going in at the beginning. So we were going in and adding 50 nodes, and then each one of them adding 5 links randomly to other nodes in the network. Plus we had the really invasive detractive process, which was taking out the top 10% of nodes based on degree. So if we take a look at the results, we can see that the spread actually reached a total of 585 nodes. Now, a lot of those nodes were probably removed, and here we can see that 500 nodes were added and 534 nodes were removed. So we're talking about a graph here that had in total 1,500 nodes. It started with 500, we added 500, and removed 500. I'm sorry, it would be 1,000 nodes, roughly 1,000 nodes. And so we can take a look at the spreading here and see what was happening. So it was a very slow start. And then we started to sort of peak around time 8, and then we really started to trail off a little bit. We were trailing off probably because we were reaching saturation. We were reaching the point where there were more nodes that were infected than not affected. We'll take a look here, and here we can see that process basically halved the average degree on this network. And we can take a look. The degree distribution is still fairly normal, but now the middle is around 2, 2.5. And now the nodes with the top degree are 5, and that's because these are the nodes that we're adding nodes with 5 links. And then this graph to show here that really once we're out around 100 nodes that have a degree of 3 or higher. So what can we conclude from this? Well, we can conclude that the random networks were pretty tolerant to random and targeted failures up until the point where we really were applying the most invasive targeted attack. and then it kind of, really sort of fell apart a little bit, or had a very slow start, and then it sort of reached that equilibrium. Scale-free networks, similar to what was observed in the error and attack tolerance paper, we saw that it was tolerant to random and the small-scale targeted failures. There was some vulnerability on the invasive attacks, but really not that much. Essentially, it delayed or it slowed down some of the beginning of the spreading process. But really, in the end, the scale-free networks, even when we were really invasive and taking that top 10% of the nodes by degree off of the network, really it was really still able to spread and spread really quickly. We saw in the random networks that it took sometimes a full 8-9 seconds for it to reach the vast majority of the nodes. The scale-free, it was almost always done in around 4 seconds or less. So does that speak to some hidden strength in some of these low-degree nodes? Probably. Where do we go from here? Well, it was a really interesting experiment, and I had a lot of fun with it. And I tried to do some things that were interesting and tried to do some things that were kind of real and maybe some things that are very unrealistic. But where I would want to go with this next is try and enhance the simulation some, increase the fidelity of it, change the order of actions and be able to specify the rates of activity a little bit differently. And maybe run the scenarios a little bit longer. You run the simulations across a longer period of time and change some of that interactivity between additions and detractions and spreading. And then use different models. Do things with links. Do something more with links. Everything we were doing in this experiment so far was just with nodes, adding nodes and removing nodes. Everything else was fairly static. And then we could talk about different spreading phenomena too. We learned about reinforcement and vaccination recovery. Adding some resilience and adding some changing, some different dynamics to the spreading phenomena and the means of spreading. And then you'll be able to track some additional metrics and some additional things. Be able to take a deeper look into what happened. See, do we have a super spreader in the network? Was it the hubs? Or was it something else? And then finally, I really would love to get to visualize this in cubics. I think you might see some really interesting things. If we could get those temporal snapshots, in adjacency matrix form and put it into cubics, probably be something really interesting to look at there. But all in all, it was a fun experiment, and I had learned quite a bit and learned a bit about dynamic networks and a little bit about robustness, and that's it. So thank you for your time, and have a nice day.